Okay, so now let me tell you about these biased voting experiments that we ran a couple of years ago, and this was loosely inspired by the Democratic primary between Clinton and Obama that was going on at the time. Okay, so biased voting. So biased voting, for the game theorists in the audience, is basically a networked battle of the sexes game, okay? So it's cosmetically similar to consensus. We all want to agree on something, but with a crucial strategic difference. Namely, we're going to deliberately introduce a tension between a desire for collective unity, which of course was present in the consensus experiments I've described, with individual preferences for the outcome, namely which color is chosen, which was not present in the experiments. And this kind of changes everything. Okay, so we're going to simplify things now. There will only be two color choices. Let's call them red or blue. And here is the basic payoff structure. If within the allotted time, and now I think we're down to 1-minute experiments, everybody converges to the same color globally. We're all red or we're all blue. Everybody will get paid something, some non-zero amount, okay? But different players will receive different amounts in the same experiment depending on what we converge to, okay? So each player is going to have a preferred and non-preferred or higher and lower payoff color. So for instance, in the same 1-minute experiment, I might be told that if we reach consensus to red, I get paid $1.50, and if we reach consensus to blue, I only get 50 cents, and you might be exactly the opposite, okay? And of course, you can also play around with the symmetry, right? It could be that my higher payoff is $1.50 versus 50, yours is $1.25.75, so in some sense, I should care more than you what color we arrive at, okay? And so again, the high-level experimental design is to choose network structures, arrange these types, i.e. the red-blue preferences, and of course it's most interesting to coordinate the arrangement of types with the network structure itself. Okay, and so this is the typical screenshot. It's the same as before, except now you're playing this game in which your payoff depends on which color we converge to, and different players have different preferred colors.
Do you know your neighbor's preferences?
You do not, okay? However, you can easily infer them, and I'll provide another anecdote here, because if you were present in these experiments in the night that we ran them, our system, the way our system works is basically the next little experiment gets queued up on your interface before the interface is actually active. So you get to kind of see for a couple of seconds what your network neighborhood looks like and what your incentives are before the system actually activates the experiment. And in that couple of seconds, before the game actually goes live, what you hear is this low roar of clicking of mouse buttons as everybody sits there hammering on their preferred color to make sure that in the first milliseconds of play, their higher payoff color is registered on the system. Of course, they might change it later. Somebody has to acquiesce. But apparently people believe, and maybe they're right, that there's some advantage to like getting your preferred color there so fast in the hopes of having some microscopic influence on the outcome. It's really quite amusing. Anyway, so I'm not going to say a lot about these, but you know, we ran experiments in which there were sort of 9 different types of network structure, which I'm showing you here, and I'm showing you 2 different visualizations of each network. One is a more traditional layout, which is just arranged by sort of, you know, whatever makes the picture look the most comprehensible. But remember, in these experiments now, every vertex has a type, namely whether they prefer red or prefer blue. And so I'm also showing you network diagrams that separate those 2 types. So in one set of experiments, we basically ran, we were in settings where we divided the 36 subjects into 2 groups of equal size. 18 had a higher payoff for red, 18 had a higher payoff for blue. And what we did was we played around with whether the connectivity was mainly within groups or between groups. Okay, so at one extreme, you could have most of the edges to other players who have similar incentives, and only a few edges of your edges, a minority of your edges, go to players of the opposite type. Okay, so this would sort of be self-confirming. Everybody would look from their local neighborhood looking like most of the people shared their incentives, even though it's 50-50 balanced exactly overall. At the other extreme, of course, you can actually create a network where everybody will perceive themselves to be in the minority simultaneously, even though, again, it's balanced 50-50. The most interesting experiments we did, I think, in terms of the results or the one result I'll dwell on a little bit on the next slide, were these so-called minority power experiments. So in the minority power experiments, we generated a network like this one, which is a preferential attachment network. And we chose the majority of players to have one color preference, say blue here, and only a minority to have a higher payoff for red. but we deliberately chose that minority to be the most connected vertices in the network. So we generated a preferential attachment network, which is known to generate the sort of a heavy tail degree distribution. So you have some very high degree individuals. We chose, say, 6 of them and gave them incentives for red against the majority will, but we made sure these 6 were the best connected. So the hypothesis or question being asked here is, can a small but well-connected minority systematically impose their will on the majority preference? And of course, that's a suboptimal outcome from a social welfare perspective, right? In this network, the max social welfare outcome is everybody choosing blue, okay? Okay, so let me save a little time here and answer that specific question. The answer to that question is a resounding yes. First of all, subjects did quite well in these experiments. Of the 27 experiments of this minority power type that we ran, a full 24 of them were successful compared to a much lower rate of success in these equally sized groups that I described also. So the vast majority of them succeeded in reaching global consensus, every single one of them to the minority preference, okay? And again, I want to emphasize that, nobody knows their position, right? The minority don't know that they have this special network position. And in fact, if you go look at the data, you'll see them kind of exhibiting uncertainty about it. So this is actually showing you a series of screenshots of play during a successful experiment. So here's sort of the red minority marked at the beginning. And you can see that, a little while later, this person has changed to their non-preferred color, even though they're in this position of power. So it's not the case that the powerful minority kind of knows it and just sits on their preferred color and waits for everybody. They acquiesce as well. Somehow, though, through network effects, it always came back to the minority preference.
Does the fraction of edges that belong to the minority determine the outcome, or is it? So something about that distribution of connections.
You mean?
In other words, so half the edges in the network belong to those 6.
I don't know. I don't know if they have the majority of the edges. It's a good question, but again, it's a good question. But I would add the caveat that even if that's true, you don't know what human subjects will make of that or what they'll do.
Another way to cast that would be to say if you balance the number of edges in the network, can you make the outcome come out 50-50 in an experiment? So that would be.
Are they really the minority?
Right. So that's another way of phrasing the question.
I'll just give you another evidence about the power of minority. So we actually have a project with a wireless provider where we are looking at the network of the basically users of these wireless networks, and we give the incentives to the ones that are the leaders, and we are reducing the churn much more effectively than just giving the incentive at random.
I see.
There is some money can be done.
Right. A practical application of this, my God.
Sorry, I've forgotten the payoff rule. If they don't reach consensus,
everybody gets nothing.
Everybody gets nothing. But then in effect, that means that if I think I have a certain cost for violating my preference, there's an infinite cost for violating the links, right? The payoff goes to 0.
Right.
So in that sense, what you said that the maximum welfare solution is for everybody to agree on blue, but of course, the worst thing that could happen is that we don't all agree.
That's right.
And so it's a slightly weird, right? The measures, the weights associated with violating a link versus violating your local preference are funny, right?
Yeah, agreed.
It's hard to.
Yeah.
You claimed that people wouldn't know whether they were well connected or not, but after a few trials, you would know whether typically you had a few, and then suddenly you have 13.
Yeah, I'm saying no in sort of I can't discount sort of people inferring things about the overall structure of the experiments, but remember, we're throwing in different network types as well. There's a fair amount of variability, I think, in what you would experience as a subject. So. You're right. They might realize, this is the highest degree I've ever had in the experiments and react accordingly.
It sounded from what you said that they would not have a clue about the network types. Do you think they can figure that out?
You mean what the overall is?
Yeah, it seems to me they would be very difficult.
I think it's very difficult.
Yeah.
I think it's very difficult.
Even though they've experienced it, they don't know what they're
Yeah, I think it's difficult. Yeah.
Potts model with local field, right? magnetic fields to different.
Yeah,
fields.
yeah.
So do you, sketch this analogy again, do you usually run some mean field?
Well,
Mind repeat the question? I doubt that it's
so he's suggesting sort of a Potts or mean field model for this behavior. Let me tell you the best model I know that doesn't involve sort of fitting parameters to the data. So actually, let me show you this. So, what's a simple model that explains some of the behavior? Let me describe it to you. So, it's a stochastic model. So, you think of yourself as a player in this game, and so you have your incentives, right? You have a payoff for red and you have a payoff for blue. Let's normalize your preference for each color to a number between 0 and 1. So basically, let's take your payoff for red and divide it by the sum of your payoffs, and let's call that your preference for red. So if it's 0.5, you're indifferent. If it's close to 1, then your payoff for red is much higher. If it's close to 0, your payoff for blue is much higher. So that's one number between 0 and 1. Another number between 0 and 1 that depends dynamically on the state of play is what fraction of your neighbors are playing red at a given instant, okay? So multiply those two numbers together, your preference for red times the fraction of neighbors that are playing red. Do the same thing for blue and normalize them to get a bias, okay? And flip a coin with that bias, okay? The x-axis here is showing you that if you take the same networks, each point here is a network, averaged over several trials of that network in the experiments. So for each network structure, we took that network structure and ran in simulation exactly the model I described to you and saw how many iterations of simulation it needed to reach global consensus. So the x and y units here are sort of incomparable. This is CPU cycles here. The y-axis here is the actual average of the behavioral time to solution on the same network structure. You can see there's a fair amount of correlation here. Like the R squared is something like, it's like 60% of the variance. So it's definitely correlated. It's a simple model that's definitely correlated with behavior, yet leaves a large amount to be explained as well.
And it's pretty mean field, like you basically took the magnetic field. And
Yeah.
In that model, it seems that indeed, if the minority controls also a minority of the edges, then that thing will not converge to the minority, it seems, because the probability, the fraction that you see in the neighborhood is basically proportional to the number of edges that the minority controls, right?
Say that again?
So it seems that in this model, if the
in the simulated model that I described, yeah.
Yes, that if the minority controls the minority of the edges, then the minority color will die out, no?
Yeah.
Sort of depends on the actual strengths of the incentives as well, right, which are kind of warping.
I have some special knowledge about this session, which is you have to catch a train in finite time.
Yeah,
and I know
so
that we'd like to have some
But the
time for
head-
general discussion too. I'm not. I don't want
So yeah, let me just push on. Yeah, these are all great questions, but let me just push on through the very last thing that I want to spend a couple of minutes on, and then we can continue. Okay. So up until this year, let me summarize what I feel like, and then I do want to spend a couple of minutes describing these very recent experiments, which I hope you'll find interesting. So at least at this sort of moderate sample size or subject pool size, human subjects, by the way, I haven't dwelled on this, but they're remarkably good. We've given them a diverse set of tasks, a diverse set of network topologies, and even though every one of these experimental sessions is wildly different, there is one common thing I can measure across all of them in the same units, which is money, right? So I can basically, for every experimental session, I can compute the maximum amount of money that the subjects could have taken from me in each little experiment. I can compute the max social welfare solution for all time across all experiments, network types, game types, etc. And then I can see how much money the subjects actually made. So the efficiency, sort of market efficiency, if you like, of the subjects across everything I've thrown at them is close to 90%. They made about 88% of the total amount of earnings possible up through last year's experiments, okay? And then you can, I've only mentioned a couple of them, but there's a lot of interesting sub-stories one can find here. For instance, network structure matters a lot and interacts with tasks in subtle, predictable ways. Small groups of individuals well placed in the network can have sort of an inordinate amount of control over outcome. We have a fair number of findings on individual subject behavior, variability, style, and personality that I won't talk about, but which you can kind of establish that, you know, despite the highly artificial scenarios that I'm shoehorning subjects into, you know, human nature and variability still shows through, right? So you can establish that despite the very limited interface that people have to communicate with each other, just sort of flickering colors, you can still come up with measures of things like stubbornness or stability or altruism and establish that indeed the variability you see in these behavioral properties exceeds what you would expect from just chance alone because of, let's say, the random assignment of position in a network, okay? There are many, many things, as you already noticed, I'm sure, that are highly artificial about these experiments. But the one that's always bothered me the most is that, you know, if these are experiments about social or organizational networks, well, in the real world, of course, those networks form organically. And they're not sort of chosen and imposed exogenously on a group of people trying to solve a task. And in particular, if you really thought about a group of us sort of starting an organization to solve some task, whether it be simple or complicated, and trying to define sort of the network of interactions that we engage in to solve that task, it's quite natural to believe that we should do even better by being able to control the formation of the network. If we're given a task and allowed to also create the network ourselves to solve that task, my default belief would be that human subjects should be able to do even better by choosing the network structure to facilitate the solution of the task rather than having it kind of decoupled from the task and exogenously imposed. So our most recent effort has been exactly that of endogenizing the creation of the network in the game itself. So this is what you might call behavioral network formation. Okay, so let me just take a few minutes to describe this, and I'll do it at a very high level and just focus on the one finding that I find most striking so far. As I mentioned, we still haven't had time to do anything but barely flick the surface of the data. So we wanted to give them a network formation task, but in service of some goal, right? We wanted them to build a network in order to do something. And so we decided to have the task be exactly the same one that I've just been talking about, namely network biased voting, okay? So the interface in these new experiments was exactly as before. Here you are, you have to choose between red and blue, you see the choice of your neighbors, and you have payoffs, you have differing payoffs for consensus, global consensus to red or blue. If we don't reach global consensus within a minute, everybody gets nothing. So it's exactly the same as before. Except in these experiments, at the beginning of the experiment, there is no network, okay? Everybody is an isolated singleton vertex with no edges to anybody else. So when the game starts, your interface just looks like you, and that's it, okay? At their option, anybody who wants to, at any point in the game, can choose to purchase edges to other players in the network at some fixed cost that will reduce your eventual winnings should you reach consensus. So if your payoff for convergence to red is $3 and you spent 75 cents on edges during the game, then you get $2.25, okay? Okay, so this is the basic structure of the game. You want to build this network in order to reach global consensus. You know what the problem is. We all want to reach global consensus, but we have to build the network in order to do it, and it costs something to build the network, okay? So you want to be parsimonious in your edge purchases, okay? And I'll let you think about what kinds of edges you want. Now, what information are we going to give people about what the vertices that they're not connected to are, right? Because if all you know is, there are these 35 people that you're not connected to, or at some point midway through the game, there's these 10 people you're not connected to, and all you can do is just say buy an edge, and the system randomly assigns you one of them. Then we're kind of baking in what kind of network structure gets chosen, right? It's going to look like a random network if every time somebody picks a new edge, we randomly. So we want to give them some amount of information about what the rest of the network looks like. Okay, so now I can describe the rest of the interface. So this interface, as before, shows you what your network neighborhood looks like, but now it changes over time. So if you buy a new edge or someone buys an edge to you, by the way, it's unilateral edge purchase, meaning that if somebody else buys an edge to you, you don't have to pay for it and you get whatever benefits, you get the benefit of seeing what that neighbor is doing, okay? So if I bought a new edge or somebody bought a new edge to me, and this was quite a complicated interface thing to accomplish, sort of a new vertex would sort of fade in on the interface with an edge to me, and then the rest of the interface would sort of, gradually shift around to try to make it the layout as simple as possible. And now that person would be in my network neighborhood. Okay, so you're sort of gaining neighbors as the game goes on. Okay, so down here though is the sort of new element of the interface, which is this is giving you information about all of the people not represented over here, i.e. the people who are 2 or more hops away from you and therefore not your immediate neighbors. And so for every one of the people you're not connected to already, there's a little white circle here on a grid with 2 dimensions. One dimension tells you what the shortest path distance of that individual is from you in the current network as it stands, and so that might change over time. And the other value tells you what their degree is. Okay, so this, for instance, is telling you about somebody who's 3 hops away from you in the current network structure and has 3 neighbors. Okay, and if there's a star here, it simply means there's more than one party of that at that particular location. Okay, and so if you want to buy an edge, if I wanted to buy an edge to this individual, I would just click here, and then my interface would change to show that person coming in, and their interface would change as well. Okay. So this is the game. I mean, one can debate, and we did, about exactly how much and what type of information you give in here. But we're basically letting you know how far somebody is from you in social distance in the current network and how popular they are. And then you can think about who you want to build edges to based on that. Yeah.
So you're also showing the connections amongst your
neighbors as before.
Even,
yeah, we've been doing that in general. You knew the connections to your neighbors. Okay. Now, I'll let you think about, if you think about this, by the way, so if to use the language of economics, this is a, asynchronous, game of partial information. So if you sort of put the adjectives together, you're in a place in game theory about which very little is known analytically. So the idea of actually analyzing this game from a game theoretic perspective, even if you try to dumb it down and throw away many of the details I described, it's basically an intractable analytical problem. Okay, but you can sort of reason at a high level about some interesting questions. So, first of all, should you buy edges or not buy edges? Remember, if enough people buy edges to you, maybe you don't need to spend anything on edges. Should you buy edges for information or for influence, right? Should I buy an edge to somebody because I think that they're aggregating information about what's going on elsewhere in the network? Or should I buy the edge in order to try to get them to change their color by seeing mine? Okay, and of course this will change whether you buy to high or low degree edges or near or far from you in the network. Should you buy edges early in the game or late in the game? So on and so forth. Okay, so what was the experimental design? So we ran a first session consisting of 99 little 1-minute experiments in which most of the networks started off the way in the initial condition I described to you, no network at all. In 36 of the networks, we decided to revisit this minority power question. And so we actually started the game with the minority power networks of the earlier experiments as the initial network, which was free to the players. So it was free infrastructure. Nobody had to buy those edges. But optionally, you could buy. So, the question we're kind of asking here is, if you now revisit this minority power setting where the minority imposed its will systematically, maybe if you let the majority buy, now that the majority can buy some edges and see what's going on more and realize that they're the majority, maybe this will change the outcome. Okay? So we ran a second set of experiments, and then a third where we did a mixture of unseeded and a variety of other sort of seed or initial networks that I'm not going to go into detail on. And let's see if this works. There's a lot going on in this diagram, but I'm going to try to explain it quickly. So the outer circle here tells you what their preferred color is, and that's going to go away when I start the experiment, and it'll be replaced by the color they're actually choosing at that moment in the experiment. Okay? So we have 18 players that prefer red, 18 players that prefer blue. The inner half moons here show you the strength of incentives. So this area is proportional to this player's high payoff for red. This area is proportional to their payoff for blue. And you can see, of course, that that's reversed for these players that have a preference for blue. And then when I start the experiment, the outer circle will show you the current color choice of the player, And then you'll also see an inner white circle in some cases that starts to occlude the inner half moons. And that's basically showing you the edge purchases of the player, okay? And so as this white circle occludes the payoffs here, it's showing you by how much those final payoffs have been reduced by the edge purchases of that player, okay? So this is an example of this setting in which the cost of building edges was rather low, okay? And so I'm just gonna go ahead and start this. This is real time, by the way. This is actually real, exactly real time. Okay, and you can see the time going across the top here. Okay, so they're done, or no, they're not done. Now they're done. So in 54 seconds, with 6 seconds to go, they reached consensus to red in this case. You can see edges were cheap, they built a lot of them. I'd like to tell you more about the topological properties of this network, but I can't. And of course, we had to we didn't know what network they were going to build, so all we can do is sort of divide the red and the blue and lay it out this way. We haven't yet bothered to generate layouts that would sort of highlight the actual structure, so you can't really see what's going on here. But you can already see some pretty fascinating things. One of them is the great variance in the expenditure on edges. So there's a huge amount of free riding going on here, right? So all these vertices with no white in them at all didn't build a single edge. And then you see some individuals who actually spent quite a bit on edges, right? They really reduced their payoffs, okay? So this just gives you a flavor of okay, so now I'm going to show you the exact same conditions, but now in which the
How much do your players learn as time goes on?
So we look for that a lot. So we look for all kinds of learning effects, but one of the simplest things to do is to look at the cumulative earnings as a function of the index of the game so far and see if it, is sort of a convex, if it looks nonlinear, right? If they're sort of making, and we've never found that in any of the experiments we've run. That's not to say that other kinds of learning effects are not present, but what we can say is that they don't seem to earn collectively a higher rate of pay as the evening progresses in any of the experiments we've run.
So is that a collective statement or individual?
Huh?
Is that a collective
This is
statement?
a collective statement.
It also looked as if the people who had shifted their views or once on average had spent more on getting information, on connecting to others.
So I'll come back to that in a second, actually. That's an interesting point that I'll come back to in a second. So let me just show you the same conditions, but now edges are much more expensive. So you see that this is, again, still real time and much slower. They're much more reluctant. Now, I think somewhat in line with your comment, notice that we have certain individuals here who really painted themselves into a corner, right? Because this player, their payoff for blue at this point is almost entirely consumed by their edge expenditures, whereas they still have a significant payoff for red. So this is an experiment that after 60 seconds failed. There was still a couple of holdouts to red, and indeed they are these people that seem to have painted themselves into a corner, right? By the way, we made sure you had an edge budget, which was such that even if you spent the maximum allowed on edges, your lower payoff would still give you some non-zero, because we didn't want people to actually truly get to the point where they get paid nothing for blue, and so they're just going to sit on red and bring everybody down, okay? Okay, so let me just now go to just a couple more of these. So this is a minority power experiment. So we've seeded this with minority power, and the edge costs are relatively low here. And you can see the well-connected minority in the middle there. Okay, and so even though there's quite a bit of network structure provided for free, you can still see there's quite a bit of edge purchasing. And this is one that rather quickly, in 23 seconds, this is unusual, reaches global consensus to the majority preference this time, which didn't happen even once in the setting where we gave them fixed minority power networks. Okay, and one more.
That's presumably because they could dilute the effect of minority power.
Okay, one is tempted to think so, but hold that thought. And here is the same setting, except now edges are more expensive. Okay, so slower rate of building now. And it's taking the game longer. The game is proceeding for longer. But now you can see the minority preference, which is blue, starting to take over. And indeed, at 59 seconds, they reach consensus to the minority preference. So this is somewhat consistent with what you're saying. But I'm sort of not there yet. I haven't carefully analyzed the robustness of the two examples I just showed you. Let's forget about the sort of seeded or unseeded distinction. How well did they do at this game? Okay, they did terribly. Okay, so in this session A, which was sort of 2/3 unseeded and 1/3 minority power, their success rate was well below 50%. Okay, nothing close to their performance in the case where the networks were exogenously imposed on them. And the minority power rate of success has gone way down. But just focus on this overall number. They did terribly at this game. I let them construct the network in service of the task as opposed to decoupling those, and they did much, much worse.
How do you know what the natural time scale is?
You mean because now they're doing two tasks rather than one?
Whatever, you decided on a minute.
That's true. Right. So, but let me come back to that a second, because we have taken efforts to convince ourselves that they were not rushed, that the problem was not that they were rushed in the sense that the cognitive load of having to simultaneously build the network and solve the task was an issue. Yeah.
The question is, after they built the network, did those networks have about the same amount of edges that the networks that you constructed did? Maybe it was still just underpopulated edge-wise because they needed...
Okay, so one thing I can assure you is that they purchased a great number of edges. So in general, maybe in the most extreme case with very, very high edge costs, it's comparable. But I mean, look at that first. The first network I showed you has many, many more edges. So I don't think connectivity was the problem here. I'm quite sure that it was not the case that there was not enough communication structure to realize what was going on in the network. But let me just push through here for a second.
To the contrary, there was too much communication going on.
I think that's closer to the truth. Okay, let me just push on here because I think people are getting restless. And I just want to make a couple of last points. So in the second session we ran, it was even worse. It was down to 38% now. So we then ran a third session in which we tried to disentangle a couple of distinct possibilities for what was going on here. So here's only two, there are others. Here are two plausible reasons why they're doing so poorly relatively at this task. One is that they just built bad networks, right? So you give them this chance to build a network to solve the problem, and they build a network that's sort of hard, okay? The other is that maybe they built pretty good networks, but in building the network, you have these people that have backed themselves into a corner, incentives-wise, and so now you have sort of a face-off, a strategic face-off, because of the extremization of the incentives, okay? So we ran a third session in which we ran 72 little experiments, in which we basically took the final networks from session A, in which the subjects had failed to reach consensus. So we kind of took the networks that they built in session A that were hard, and we basically, we both did these in which they couldn't buy any edges, in which they could buy one to sort of have some cognitive comparability to the edge purchase scenario. But most importantly, we ran all these experiments from two initial conditions. One is one in which the incentives on the hard network were the initial incentives of the players from session A, and the other one is when they're in the final, when it was the final incentives, okay? And the bottom line is that they still did poorly in both of these settings, even when we reset the incentives to the initial ones, so that if a great network had been built, but that the people who built it were too stubborn to reach consensus, not true. They still did absolutely awful. Okay, so my top level conclusion of this is that people are great at everything I've thrown at them, except when I gave them the opportunity to build the network to solve the task, their performance got radically worse. They seem poor at building networks, even though they're very good at solving a diverse set of problems across a diverse set of exogenously imposed networks. So it's late, and I know people probably want to get to the reception, and I'm happy to take more questions, but let me just put up these conclusions, and thank you for being a great audience. You asked a lot of great questions, and I'm happy to hang out.
All right, maybe we should have two questions before we go outside, and then as much any round enjoyment as we feel like. Yeah.
it takes time to develop a strategy to build a good network. How much time did they actually have to think about the process?
You mean within each experiment? So a maximum of a minute. But anecdotally, I would report that many of the experiments look like the ones that I showed you here, which is that in the first, there's edge creation going on throughout the 60 seconds, but the bulk of it, by far, the vast majority of it is in the first 20 seconds or so. So I think in general, the network structure is largely in place by well before midway through the experiment. And so they're choosing to do that quickly, and then they have kind of 30 seconds to kind of work through the consensus problem on that network.
Possibly
Possibly, yeah.
One last public question.
You want to pick it?
Sure.
Well, let me pull back and ask a more general question, because there are a lot of these models, I think, like the web graph and attempts to model them. And of course, Erdős rating doesn't work there because you see the different degrees and things like preferential attachment. And in the beginning, you talked about power laws, but what about the possibility that people are just trying to push the real data into the mathematical model? I mean, what about the sense that maybe these things don't have power laws, but we're really just trying to look at these?
You're talking about the broader yeah. So okay, you asked an excellent point, and it is a subject of ongoing controversy. In fact, some of you may be aware of this paper by John Doyle and Walter Willinger and others that basically claim that all these power laws we're observing in nature are an artifact of the way that we process data. Having to do, like at a high level, you have to bin, if you want to go out and measure the web graph and talk about its degree distributions, you have to bin those degrees into the buckets. And the claim is that these kinds of very processes of just statistical data analysis are inclined to bias you to find power laws. So I think, I think I see less debate around the question of whether the distributions are heavy-tailed generally, i.e., poorly fit by Poisson in the particular aspect of having a heavier tail. That seems to me relatively uncontroversial. Whether these things are actually power laws per se or are better fit by a log normal, I'm agnostic, and there seems to be debate, and it seems to me kind of irrelevant to the broader picture about the fact that, why do you get things that are consistently so unlike a Poisson process in this particular sense? But I think it's, I do think there was a bit of a cottage industry for a while of people going out and marveling at, it's a heavy-tailed distribution, it's a power law, and it's got this clustering coefficient, and it's got this diameter, and there's the pages of Science and Nature are littered with kind of descriptive analyses of that form. And I think I credit that series of descriptive analyses with drawing attention to the possibility that a wide range of naturally occurring networks might share remarkable structural properties, but I wouldn't want to stake my life on any particular parametric form for those properties, for sure.
I want to close this and thank you all for coming.